All right, let's start replacing some components and see how many times I can hit this camera here with my shoulder. All right, so I'm going to just start out by replacing these transistors right here. And I just noticed I don't have the outline. I want to make sure I have the pinout correct on these. I'm pretty sure I know what it is, but I don't want to connect it the wrong way. So there is a diagram here in the service manual that shows you the proper pinout of the transistors, and here it is. I just found it. And you can see how these are laid out. So the first one we're going to replace is this 2SA979. And that's going to be the input pair right there. And you can see it goes, they're considering the wedge or the tapered part in the front there, they're calling that the front. So base, collector, emitter, collector, base. So the bases are on the outside, the collectors are the next in, and the emitters are tied together. So we have to make sure that the transistors that we use will be configured in this same way. So in order to do this correctly, they're going to have to be put together in this manner, like this. And you're not seeing a daggone thing, are you? So you could see how those are right like that. So the emitter, so it goes emitter, collector, base. So if I have this one facing the other direction, it'll go emitter, collector, base that way. So if we try to kind of hold this, we will have base, collector, emitter, collector, base. Now, the way these are shaped, kind of rounded, they can kind of fit together like this. So we can get thermal coupling. And by the way, I did match these transistors. They are perfectly matched. And it's funny, I pulled these just straight off of the strip, out of a big bag of them I have, stuck them in the, in the comparator, and they came out one of the best matched pairs that you can have. I mean, again, when you get these gain binned transistors, that have the, the letter after them within the gain range and so forth, they're usually, if they come off of the same production line, they're always going to be pretty close. Even if you don't have a means to properly match them, a lot of times they'll be pretty close, and they'll be close enough. And actually for this transistor, it's not that important that they're matched. And I'll explain that in the schematic here when we get to that part. But right now, let's just assemble this. Okay, we'll just tack these together in the middle. That's it. I think I got it. Yep. It appears, anyway, as though I have. And you want them to be touching like that, just a little bit. They'll get together a little better. Then I'm going to take this pretty piece of yellow heat shrink and just cut it off. And I'm going to take some thermal glue, which always gets all over everything. Get a paper towel here. And these transistors were perfectly matched. You don't really have to match these things a whole lot if you buy the ones that are already gain sorted, that they have the numbers after them. They'll say things like, it'll say KSA992, and then there'll be a letter after that, F or G or H or something. That is indicating the gain sorting range of that transistor, and they're sorted by their gain. So what ends up happening is when you when you just pull them off the strip, they're going to be pretty closely matched, close enough for this type of circuit that you really, very rarely do you get, very big differences from one to the other when they're numbered like that. So I know people like matching transistors. I like it too, it's fun, but really not necessary. So that thermal glue will harden, and it will combine those two transistors into like one package as soon as it dries. And you can see it'll smush out as it cures. But that's it. Now we have a a two transistor package, just like the ones, the original ones. Now for the current mirror, those are NPN transistors. You can see down here. And we're going to use KSC 1845. So KSA 992s for these and KSC 1845s for these. And they are wired differently than their PNP counterparts. So if you look on this one, you can see how the bases are on the outside and the emitter is common. This one, the bases are common and the emitters are on the outside. So we're going to have to orient these differently. So in this case, it goes emitter, collector, base. So we want to turn this one this way, like that. So the bases are now tied together. Okay, I went ahead and made the NPNs as well, just because I had everything out to do it. So now we have the transistors for both sides, and they're all done. And as soon as that glue hardens inside there, then we can go ahead and install them. So I'll put these back, and I used yellow for the PNP, and I marked them, and then the black would be the NPN, because once you get these together, unless you test them, you won't know which is which. And I want to make sure those are good. Okay, so that's done. Okay, let's start replacing these components. Take the schematic. So we make sure we know what we're doing here. And let's start out by, let's just get these little transistors replaced. Okay. Let's replace this one. First one I'm going to do is this 2SC869. It's an oddball transistor. Not a whole lot of data sheets and things. There is information out there on them, but another one. All of these transistors here are odd, numbers, and not real common everywhere except in this audio industry. I'm going to replace this with a KSC 2383. Much more, it's a very robust transistor. This is something that's part of the protect circuit. So we want that to be very reliable, and we want it to have similar characteristics. So this will work perfectly in there. And I think this also goes emitter, collector, base, but I just want to make sure. I don't have them all memorized. I don't have a whole lot of anything memorized. Let's see. There goes emitter, collector, base. All right. So we want to go, let's see. The emitter's on this side, so we want to go this way. And if I go off camera, you'll just have to forgive me because I'm not always paying attention to where the camera is. So you have your choice when you do this stuff, and when you're making videos. You can pay attention to your camera work and all that, and notice how this one is oriented different. This one's probably emitter base collector or something like that, or collector base emitter, I don't know. No, it's, yeah, see, it's base collector emitter, so it's flipped. You have to watch that. I mean, even though the transistor is electronically the same, it may have some physical differences, and you have to always check that. Always, always, always. All right, let's get this put in there. And yes, I could probably remove these wires, but they're not, this isn't a big job to redo this. I mean, doing it on camera makes it seem like this is a lot bigger deal than it really is. But really, you could kind of buzz through this pretty quickly if you didn't have a camera in your face. And it's not worth unwiring all these wires just to do that. So, put that in. And that's it. One down, a bunch more to go. Okay. Now, I'm going to replace this transistor right here, and it happens to be this Q1 right here. This is actually thermal tracking for this transistor. So what this will do is this will compensate for thermal changes in the transistor. So as this transistor heats up, its VBE will change, and as the VBE changes, it will affect the current gain, and it could actually throw this center point off. You want this input to be 0 volts. You want 0 volts on both sides of these with no signal. And what will happen is, as this heats up, all of this biasing in here will change a little bit, and this will drift up or down and put a tiny little bit of offset on it. And you know, we have a current mirror in here, and of course you have your resistors that act as the tail, which is your current source. And you could put an active current source, you know, constant current source up there in place of those resistors, which some of the other designs out there do. But this is even better. And what this is doing is this is making sure the midpoint stays at 0 volts, even if this transistor drifts. And that's why I said, if these are not perfectly matched between this current source, the current mirror down here, the current source, which is this tail resistor, and this thermal compensation circuit, even if they're slightly, out of match, they're not perfectly matched, this is all going to hold everything in. And it's kind of a unique circuit, because you would think what's going to happen, you would think maybe that this thermal transistor will fight the circuit. So like if you start applying a signal here to the input, why doesn't this affect the offset because of your signal you put in? Because it's not 0 volts anymore because you're feeding a signal. Well, that's the job of this little capacitor right here. And we'll go over a little more of this theory later, but it's pretty interesting. So this capacitor will bypass the AC, but at DC level, this transistor will be active. It's kind of what this is for. That's why it's such a high value. See, it's 100 microfarads at 35 volts. And you can see this is a relatively low current circuit, because look, you have a 15K, 150K pot, and then an optional 100K resistor that you can pull the jumper. And the whole idea is you want this to be a real high impedance. You want it to hold this to 0, but you don't want it to be affected by your input signal. And we'll see how this all works. So this not only acts as thermal compensation, but it's also your midpoint set. So you can actually, by adjusting this resistor, this is what sets your DC balance or your offset adjust at your speakers. Very elegant circuit. I really like it. And it's simple too. There's not a whole lot to it. And I have a simplified diagram. We'll go over it later. And this is a 2SC1775, and I'm going to replace it with a KSC1845. These transistors on the front here have to be the 992s and the 1845s. Number one, these are low noise transistors. Number two, they're high gain. And number three, they have a high voltage. Most of these are rated at like 120 volts. And you got to realize you have a 68 volt supply and a minus 68 volt here. You're never going to see that full difference on across these, but you will see some pretty high voltages. If you go to like what's over here, the 2SA733 and the 2SC945s, these have a lot lower voltage rating. And the KSAs that are replacements actually have a lower current rating than the original 2SA. But in this circuit, very, very low voltage. So these are actually the proper component for that. But anyway, let's get it replaced. Okay, the next thing we're going to move to is these driver transistors, and we're going to do something a little bit different with them. First of all, the best replacement that I have for these is an MJE15032 and MJE15033G. They are a really good replacement for these, and they're actually rated, spec'd out better than these. These are pretty important because these are what are connected to your main output transistors, and they're going to carry, next to the output transistors, these are going to carry the most current. That's why they're up on heat sinks. Now, the way they mount them at the factory, they put some thermal grease and then they directly couple them to the heat sinks, which is fine. Actually, that gives you really good thermal transfer. The problem is the collector of both of these transistors is now connected to these heat sinks. And while these heat sinks aren't touching anything, and that's fine, if something does touch these two together, you're shorting the two collectors of the transistors together. So you can see we're talking about these transistors here. So if you shorted the collectors together, you are now shorting the negative 76 and the positive 76 voltage rails directly together. And all it takes is a slip of the screwdriver or one of these components to touch, and that can happen. Is that very likely to happen? No, especially when it's installed in the amp and working. But when you're in there probing around and things, it is possible to do that. So I'm going to put thermal pads and these little washers on there, if you can see where I'm at, and I'm going to isolate these heat sinks. These actually have a much better thermal transfer coefficient than mica, and they will be every bit as good as the thermal grease, if not better. So no problem there, and these are small heat sinks in the first place. So just going to have a little bit of electrical isolation, and that's just for a little bit of extra safety. Plus I don't have to deal with the grease and get it all over my fingers and everything. Okay, I am going to use this screwdriver to take this out. Why, you might ask? Because my 3-year-old grandson actually went to the hardware store and picked this out and said, I want to give this to Papa for Christmas. So I'm going to use my Christmas present from my 3-year-old grandson to work on this, because it just makes it more fun that way. How about that? And it actually fits these screws really well. I'm quite happy. His dad is a brilliant person himself, and he's really good mechanically and so forth, and I think he's going to take after his dad. Hopefully he won't take after his grandpa, because, then he'll be forgetting everything like me. Okay, let's take this out, and then we'll put the new one in, and we'll clean everything up, and we should be in good shape. Again, these transistors are probably good. There's nothing wrong with them, although I do think the input pair transistors are noisy. I noticed that when I tested this amp out. Part of that, again, could be due to the dirty controls and things. But some of that, when I was listening to it for a while, some of it appeared to be, you know, shot noise from the transistors, and that's pretty common with those. So you can see how cruddy that is. It wasn't making super contact to the heat sink. These little thermal pads actually help it a little bit, I think. And this is glued on there. I'm going to pop the glue off right now, and I'm going to clean this thoroughly, and then we're going to put the new one in. Okay, and just make sure that it's, again, this doesn't have to be like this. I'm doing this because I want to, and because I want, see, no shorts there. So, you know, from the screw to the heatsink is a short, but from the flange to the screw is no short, and from the flange to the heatsink is nothing. Yeah, I know that was awkward how I was holding that there, but hey. Okay, so that one's ready to go in. We go. Okay, I'll get these 4 along here, and this is part of the overload protection circuit. They're very, very low voltages on there, really. You can see the big resistors they have in there and so forth. And the idea is that these will limit the amount of drive into the inputs here. There's 2 methods of that. Number one is these transistors here. So if you have an overload in here, either on the positive half cycle or the negative, these will actually clamp down the base of the input of the Darlington pair there, and they'll just kind of come in as they need to. The other thing is these diodes here, D6, D2, D5, and D7, and what those do is those will also limit the maximum voltage so that you can never overdrive this circuit from this circuit. It just keeps everything in line. So you have these diodes here and then this transistor network. So you have 2 different forms of over voltage and over current protection. Okay, I have a little smorgasbord of different capacitors in here, and each one suitable for its purpose. I'm going to start out with the input capacitor. This is the input to the amplifier. So that would be this one right here. And that's where the signal comes in from the preamp. And this is one of those orange ones, and these are low noise, but they actually develop leakage over time. Of course, who knows what I'm going to be like, you know. I know as I reached the same age as this capacitor, I wasn't what I used to be either. So, and again, these were fantastic caps, but these are very purposely built. These are made for audio. And the closest thing you can get today is these Nichicon UKL or KL series. That's what I use. They are also a low noise capacitor and a low leakage capacitor. And yes, they are electrolytic. And no, I am not putting a stacked film capacitor in there, because actually the way that film capacitors react to different frequencies and amplitudes is different to how a electrolytic will. And that's why you see electrolytics. A lot of people think it's because electrolytics were too big or whatever. This is only a 1 microfarad capacitor, and really, you know, film caps like this, as you can see, existed back then, but they did not use them in that position. There's a reason for that. So in this instance, I will replace these with a UKL. You can also use a FG series would work. Even probably one of these KT series would work. If you have the Elna Silmix, those are great. The black gate caps that are impossible to find, but ones that are made for that purpose. And then when we get to this tantalum, I will replace that with a film capacitor, because really these are all about having extremely low ESR and leakage. And this one's most definitely going to be good, but tantalum caps have a way of shorting out after a while sometimes. So I'll put one of these film caps in. This is just a timing capacitor for the protect circuit, so it doesn't pass any audio or anything like that. So this film cap will work perfectly in there. For those of you who might ask, and I know I always get comments, regardless of what I say, somebody will come on and say what I already said or ask about it. But truth be told, I have used film caps in these, in the audio path like this before, substituting for a electrolytic, and they work. But even with my really bad ears, I hear a very distinct difference in high frequency response. And it isn't something imagined. You can actually hear it. It's the sound is, more shrill, I guess you could put it. You will notice a difference, especially on a really good set of speakers that are very efficient. You'll notice that a little bit. Now, some people like that sound. They say it makes it sound clearer to them. I have really bad ears. As a matter of fact, I'm supposed to be fitted for a pair of hearing aids. I'm probably going to, at the beginning of this year, going to do it. My hearing's really bad. But that being said, I can hear the difference on those. And I don't say that very often. There's a lot of snake oil out there, and there's a lot of urban legends about different components sounding different or whatever, but this one is pretty easy to, anybody who's really experienced it, it's not real hard to notice the difference. Okay, board number 1 is finished. Couple quick notes. These worked out really well. I did have to take a pin vise with just a tiny bit and just go one size bigger on the middle hole just to make it a little easier. They would fit in there, the pins would fit together, but remember there's 2 pins in that middle pin. And I think it looks good. The potentiometers, the one that I had for this one is kind of a special one. It's a 150K pot. And the ones that I have only go in 2s, so I could have a 200K, or a 100K, but I can't have 150K. So what I did was I put a 200K pot in there. I had to drill the middle hole out because these are triangle shaped mounting holes, and these ones were linear. So again, I took the pin vise, I put a center hole in between and just bent the pin over. And if you notice, I put a 1 mega ohm resistor across that 200K, and that makes it pretty close to 150K. It's not exact, but much closer. And of course, we have the jumper that we can always remove if we don't have range. The other thing I did was with both of these pots, I measured the old ones prior to removal, and then set these ones to the same setting as the originals. Just makes it a little easier down the road to get you in the ballpark. Although, after replacing all the semiconductors, it wouldn't surprise me if they would be out of adjustment anyway. Anyway, there it is. It's done. I'm going to do the same thing to the other board, and we'll be ready for the next stage after this. So that's the end of this part. I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again in the next part. Take care. Bye-bye.